Hello everyone, welcome to join us. Today we are going to talk about the deep reinforcement learning, the theory behind AlphaGo, the program that beat human Go champion. Deep reinforcement learning is one of the most exciting research fields in recent years. What is reinforcement learning? In its simplest form, reinforcement learning is trial and error plus delayed reward. Trial and error means learn from your own mistakes, while delayed reward means our goal of learning is to maximize the cumulative reward in the end. In fact, there are a lot of reinforcement learning examples of animals. For example, let's think about a baby that tries to learn how to walk by themselves. They will keep falling and standing up many times until they learn how to walk. However, there's a big difference between today's reinforcement learning algorithms and the animals' learning. That is, animal and human can learn from very few examples. This is an unsolved problem, and we still don't know why. The possible answers are maybe that animals have some pre-programmed algorithms in their brain after the 230 million evolution, or humans can do imitation learning by observing other humans, or that we need better algorithms that current backpropagation and gradient descent. Let's define reinforcement learning mathematically. First, there is a software agent and an environment. The environment provides observations and rewards to the agent. Observations is also called state, ST. The goal of the agent is to learning how to perform different actions under different state in order to achieve maxima cumulative future reward, RT, in the future. In other words, the soft agents learn an optimized action model in an environment by doing trial and errors million times. The model is also called policy. We can use conditional probability to represent policy. So policy can give us the probability of perform action AT under the observation ST. There are many kinds of environments and actions as listed in this slide. Chess is fully observable, which means that we can observe all the actions of our opponents. On the contrary, the video game StarCraft is only partially observable. The other characteristic is if the learning is performed by a single agent or collaborative learning of multiple agents. The simulation environment developed by MIT professor Lex Friedman. By the way, many slides are extracted from his lecture. Deep traffic. The simulation environment deep traffic developed by MIT is an example of multi-agent learning, which is shown here. Another characteristic is whether the environment is deterministic, like chess, or stochastic, which has some randomness in the environment, like deep traffic. Finally, the environment can be either discrete or continuous. Reinforcement learning can be formulated as Markov decision process, NDP, which is a discrete time stochastic control process. Here is a figure of NDP process, which extract from the Wikipedia. NDP has widely used in many disciplines, including robotics, automatic control, economics, and manufacturing. NDP were proposed as early as 1950s, and provides a mathematical framework for modeling decision-making in situations where outcomes are partly random and partly under control of a decision maker. NDP are useful for studying optimization problems solved via dynamic programming and reinforcement learning. In this figure, at each time step, the process is in some state S, and the decision maker may choose any actions, A0 or A1 in this case, may choose any actions that is available in state S. Once you choose an action, suppose it's A0, you have you may be randomly moving into new state. In this case, we have 0.5% probability to move to to go back to state 0, or 0.5 probability go to state S2. Each action, each random result will give us a reward. Here this is -1 reward. Here is +5 reward. So this process is partly random and partly under control. This is Markov decision process. Here is an example from David Silver's class. He created a student MDP Markov decision process example. In this example, a student first go to class 1. After the first class, the student may choose to do Facebook or continue to join the next class, class 2. If you can insist to go to class 3 and continue studying, then you will pass the class and get the reward +10. And then go to the final state, the terminal state, sleep. Sleep is the terminal state of the student MDP. So once we reach terminal state, we will stop here. On the other hand, after class 3, you may choose to go to pub and relax. Then after the pub, you will randomly go back to review the material. Maybe you have a discussion with your friends. So you may decide you have 20% probability to decide to go back to review the material of class 1, or 0.4 probability to go to review class 2, or 0.4 to go to class 3 and continue to study the material of class 3. And finally, you may again choose pass the class and get the final reward +10. We may notice that there are many minus rewards. It's very natural in reinforcement learning. For example, doing Facebook will hurt your learning, so you get -1 reward. But however, study may also hurt your feeling, so you may get -2 reward. After the first 2 classes, that's very similar to real life. Study is painful, but you will finally get your reward in the end. Let's look at another type of reinforcement learning, which is related to chess game. Consider the familiar child's game of tic-tac-toe. 2 players take turns playing on a 3x3 board. One player plays X and the other plays O's, until one player wins by placing 3 marks in a row, horizontally, vertically, or diagonally. As shown in this figure, the X player has won because it plays 3X diagonally. If the board fills up with neither player getting 3 in a row, then the game is a draw. Because a skilled player can never lose, let us assume that we are playing against an imperfect player, one whose play is sometimes incorrect and allows us to win. When playing game, our move will affect opponent's move, and the opponent's move will affect our move. This process can be expanded into a tree structure. If the number of states is small, we can exhaustively calculate all the winning probabilities. First, we will set up a table of numbers, one for each possible state of the game. Each number will be the latest estimate of the probability of our winning from the state. We treat this estimation as the state's value, and the whole table is learned. It's called the value function. We then play many games against the opponent. We move greedily, selecting the move that leads to the state with greatest value, that is, with the highest estimated probability of winning. Occasionally, however, we select randomly from among the other moves instead. These are called exploratory moves because they cause us to experience states that we might otherwise never see, and let us learn other playing strategies. While playing tic-tac-toe, we keep updating the values of the states V of st. Higher value means that we have higher chance to win in the future. So our learning goal is to make the value more accurate, estimates the probability of winning. To learn the values, we would first play the game to the end, and then back up. We need to play to the end to see if the results is winning or losing, and then we back up the value of the state after each greedy move to the state before the move. The red arrows means the value update. Here is the formula of updating values. We will calculate the difference of later state, V of state t plus 1, which means the future step of current state st. We will use the next step st plus 1 minus the current value. This is called the temporal difference, and we will update the difference to our current state by a learning rate. So the basic idea of value function is to calculate the difference between the next step and the current step, and then use the temporal difference to update our value table, our value function. All kinds of reinforcement learning algorithms can be viewed as a searching along width and depth of the MDP expanded tree structure. The record of each depth searching is called a trajectory. All reinforcement learning methods have three key ideas in common. First, they all think to estimate value functions. Second, they all operate by backing up values along actual or possible state trajectories. And third, they all follow the general strategy of generalized policy iteration, meaning that they maintain an approximate value function and an approximate policy, and continually try to improve each other on the basis of the other. These three ideas are central to the subjects covered in Sutton's book, which is the Bible of reinforcement learning. As shown in this figure, the most fundamental learning algorithm is temporal difference learning. The formula of temporal difference learning has been shown in previous slide. If we decide to go to the depth first, to expand all the possibilities in the depth first, it's called the Monte Carlo method. For example, for learning chess, we would like to plan chess to the end of the game and back update the values of previous value function. So for Monte Carlo method, we will plan to the terminal state and then back update all the value functions. Another dimension is width update, which means we will evaluate all possible actions at this state and then calculate, then updating the value function. This is called dynamic programming. So updating the value function is very much like a search on a tree. If we decide to go depth first search, then it's called Monte Carlo method. If we decide to do width first search, then it's called dynamic programming, which means we evaluate all the possible actions of this state, of current state. But if we have a lot of time and computing resource, we can do exhaustive search to evaluate all the possible actions and all the next state, all the terminal state. This is called exhaustive search, but it's not practical in real applications. So usually we are choosing between Monte Carlo or dynamic programming. From different perspectives, the horizontal dimension is sample updates between sample updates, which is based on sample trajectories. So if we use temporal difference learning for one step or multiple states, we will have a lot of trajectories. It's called sample update. We will use the trajectory, which is actually the experience results. Playing result is called trajectory to update the value. Or we can use the expected value based on the distribution of the probability actions probability. So it's called expected update, but this requires action probability distribution model, while the sample update only need a sample model. It can be done from actual experience with no model at all. The vertical dimension corresponding to the depth of update, that is, to the degree of bootstrapping. So it's called bootstrapping because it will play the states by itself and back update the value function. So at the three corners of the four are the primary learning method, temporal difference learning, Monte Carlo, and dynamic programming. The exhaustive search is just the extreme case that it's running so deep that all the terminal state has been visited, and we can help you calculate all the probabilities. But it's just the extreme cases, not for real application. All reinforcement learning algorithms face the exploration and the exploitation dilemma. Exploration means that the agent tries to search for new ways by taking random actions. Exploitation means that the agent follows current policy and selects actions greedily. That is, always select the current best action. Exploration tries to find better strategies, while exploitation focuses on improving current policy. The most common method is epsilon greedy, which performs random actions epsilon at a time and perform the greedy actions 1 minus epsilon of the time. The figure to the left means the exploration, which means our algorithm like to explore new possible ways. And the figure to the right means exploitation, which means we select the best current approach. Selecting current best action is called the greedy method. So there's a lot of money means this is a greedy method. Now we know that all the learning control methods face a dilemma. They seek to learn action values conditionally on subsequent optimal behavior, but they need to behave non-optimally in order to explore all actions and find the other possible optimal actions. So how can algorithms learn about optimal policy while behaving according to an exploratory policy? So there are two kinds of learning policy. The first is on policy. On policy means that we use a greedy algorithm, epsilon greedy algorithms, which means we have the epsilon randomness to explore. We have to explore random actions epsilon of the time. But it's actually a compromise. It learns action values not for optimal policy, but for near optimal policy. But it's simpler and fast to converge. However, it's to local minima, it's more difficult to find global minima. So it's tempted to converge to local minima. On the other hand, there's another approach called off-policy. Off-policy is actually used to policies, target policy and behavior policy. So target policy now is our current optimal policy, current best policy, and the behavior policy is more exploratory. So we allow the behavior policy to try more different random actions and update to the target policy after a period of time. This is called off policy because the learning is from data of the target policy. So the overall learning is used to policy. So it's harder to train because we have two policies now, but it's more powerful in the long run. In the beginning, the on policy may converge faster and have better performance, but in the long run, the off policy will get better performance because it can keep the optimal policy while let behavior policy to explore more options. Let's look at a maze learning example. This example is from the first class of David Silver's reinforcement learning. The objective of the agent is to find the shortest path between start and the goal. Here's the possible shortest path. To let the agent learn the shortest path, we will give the agent -1 reward or negative reward per time step. So it encourages the agent to arrive at the goal at the shortest time, which means it will have less minus reward. There are 4 actions moving north, east, south, and west. The states are the agent's location. Here is how the policy function looks like. A visualization of policy pi of AT under the condition of state T. In this example, the red arrows are the actions. The red arrows are the actions of the agent choose to do under different state. This is a deterministic policy, which means we always select one specific action at a specific state. So if we learn the model, we train the model successfully, the policy model will show us which action has highest probability to achieve a long-term highest value. So follow the direction of the policy model, we can find the shortest path. In this case, this is policy function. On the other hand, we can learn the value function of each location and use the value function to choose our action. Let's look at the value function of the map. We can start from the location nearest to goal. We have -1 reward because it will take only one step to reach the goal. So only one step we can reach the goal. The value is -1 reward. By moving toward the location of a higher value, we can find the shortest path. So in this case, the second location is -2 because it takes us 2 steps to reach the goal, right? And -3, -4. So the star has very high minus value, -16. So now we suppose our agents start to work to the goal. then we will choose the position that has highest value, which is the minus 15. And then in this position, we will choose the next position with highest reward, which is minus 14. Then follow this value function, follow the greedy policy. We will always choose the one with highest reward. We can also find the shortest path. The third approach is to build an internal model of the environment, which is very much like drawing a map by explore the environment. In this case, the agent build an internal map of the environment, and then the agent can find a way to the goal. For example, after hundreds of tries, the agent may have found a path. This is called a trajectory of reaching a goal, and give each step a -1 reward. So once we have an internal model, we can use the model to plan the shortest path. From previous examples, now we know that the reinforcement learning algorithm can be classified into 3 types: the model-based methods, the value-based method, and the policy-based methods. Most reinforcement learning algorithms are model-free and belong to value-based or policy-based, such as DQN belong to value-based, and the policy gradient is a policy-based method. Some algorithms are a mix of 2 types, such as Actor-critic. If we have a good model of the environment, then we can use the model to plan the actions, and the learning will be very efficient. We may just need to play in an environment 100 times. It's called time steps. 100 time steps and achieve the good result. However, it's difficult to learn the model of a complex environment in practice. So usually we prefer other 2 methods. The value-based method learn a possible reward, which is called the value of each state, or even the state action value. It can learn the state value or the state action pair value. And then we can act by choosing the best actions which has highest value in next state. We need to add exploration in the value-based method. For our policy Q-learning, we may require around 1 million time steps to achieve good results. So value-based, we need more training steps than the model-based method. The third method, policy-based method, is directly optimize the policy function. The policy function will generate the probability of selecting actions. So we just act by sampling the probability output of our policy function. The exploration is baked in. However, the policy-based method requires much more training steps. Like the unpolicy policy gradient method, it requires around 10 million time steps, or even for other algorithms, it requires 100 million time steps to achieve acceptable results. And the popular methods now is the mix of value-based and policy-based, called Actor-critic, and it's a balance between the value-based and the policy-based method. This is the reinforcement learning taxonomy from OpenAI. This tree diagram includes most state-of-the-art reinforcement learning algorithms. OpenAI first classify algorithms into model-free and model-based. The policy optimization and the Q-learning belong to model-free reinforcement learning. The most famous Q-learning based algorithm is the deep Q-learning (DQN). Other popular algorithms of policy optimization include the policy gradient and the actor-critic method, asynchronous actor-critical method. A3C is the asynchronous actor-critic agent, and A2C is synchronous actor-critic agents. Those are very popular methods. For model-based reinforcement learning, there are word models or other algorithms. One special case is AlphaZero or AlphaGo, which are given the model because we know the rules of the game Go, right? And the chess game are fully observable. So chess game are actually we have the model of the chess games, and they are simplified learning problem. Let's introduce the most popular value-based method, Q-learning. Q-learning learns the values that can estimate the expected future reward for different actions under various states. We can formulate it as a Q function of state and action. Q refers to the quality. We can update the Q function using Bellman equation. It's very much like the temporal difference learning. However, note that we use the maxima value of next step Q value as our target. So this is an off-policy learning method. If the number of states and the number of actions are few, we can build an action state table. Here's the action state table, which is also called Q table, to calculate the corresponding rewards of each action and the state pair, as shown in the lower left corner. However, the number of states are very large in real world. It is inefficient and nearly impossible to build a complete action state table. So DeepMind solved this problem by using neural network to approximate the Q table. Their method is called Deep Q Learning, DQN. About policy-based method, the most popular algorithm is policy gradient. Policy gradient is an intuitive method that directly optimizes the policy function. This is an on-policy function because we only have one policy function. Compared with the off-policy methods such as DQN, policy gradient is easier to train and converge, but also tends to stuck at local minima. Andrew Karpathy has made a very interesting introduction experience of training agent to play game Pong using policy gradient. For more details, you can refer to his GitHub. Here is the formula of policy gradient. We usually calculate the log version of the policy function, which is usually softmax, because softmax can give the probability of each action under different states. Okay, so we get the log version of our policy function and then calculate the gradient. The final loss function is the expected value of the policy gradient. So this is the policy gradient formula. Another important branch of reinforcement learning is the actor-critic method. The two most famous actor-critic methods are A2C and A3C. Let's take a look at those algorithms at the next page. The actor-critic method combines the policy gradient and the Q-learning. In other words, it combines the value-based method with the policy-based method. So there are two parts. One is actor, which decides the actions to take under different states. And another one is critic. Critic measures how good the action was and how to improve. Depends on the types of the value function. The actor-critic network can be classified as Q actor-critic, advantage actor-critic, or temporal difference or TD actor-critic, based on the value function we use. DeepMind proposed the asynchronous advantage actor-critic method, also called A3C. There is a global network parameters and there are a lot of agents training in parallel. There are multiple agents run parallelly in their own copy of the environment, and then update the global network periodically. The updates are not happening simultaneously, so that's why it's called asynchronous. After each update, the agent resets their parameters to those of the global network and continue their independent exploration and training for n steps until they update themselves again. We see this information flow not only from agent to the global networks, but also between agents, because all the agents experience will partly be added to the global network parameters. So the A3C can efficient learning on the multi-core computer. For A3C, we usually use CPU to train the agents, not the GPU. On the other hand, the OpenAI suggests that synchronous update may be more efficient, but we need to add a coordinator. This algorithm is named A2C because it's now synchronized version. It's synchronized advantage actor-critic A2C. A2C outperforms A3C on many reinforcement learning benchmarks. Training reinforcement learning model is very difficult, like other deep learning models. Here is a trick called the trust region policy optimization, which can help to stabilize reinforcement learning training. The idea, or the basic idea, is to avoid taking bad actions that collapse the training performance. TRPO updates policy by picking up step size that satisfy a spatial constraint on how close the new and old policies are. The space is called trust region. The constraint is expressed in terms of KL divergence, a measure of distance between probability distributions. This is different from normal policy gradient, which picks a direction first, then step size. In practice, a single bad step can collapse the policy performance. This makes it dangerous to use large step size with traditional policy gradients. TRPO nicely avoids this kind of collapse and attempts to improve the performance quickly. In previous slides, we have learned the basics of reinforcement learning. Now let's talk about the recent advances in deep reinforcement learning. Deep reinforcement learning are largely made by the DeepMind company. DeepMind was founded by David Hasselbeis, Shem Lek, and Mustafa Suleyman in 2010. The goal of the founders is to create a general-purpose AI that can be useful and effective for learning almost anything. Because the founders has background in game industry, they start training AI agents how to play old Atari games that were popular in 1970s and 80s. On January 26 in 2014, Google announced the company has acquired DeepMind for $500 million. The company made headlines worldwide in 2016 after its AlphaGo program beat a human world champion Go player Li Sudong. DeepMind published their first breakthrough algorithm, DeepQ Learning (DQN) on Nature. The title of the paper is Human-Level Control Through Deep Reinforcement Learning in 2015. Here are some examples of AI playing Atari games in OpenAI Gym. OpenAI Gym is an open-source reinforcement learning simulation environment released by OpenAI. We will use OpenAI Gym to try some algorithms later. When training AI playing Atari games via reinforcement learning, the environment is the Atari game console. Here is the picture of the game console, which was made in 1970s. And the reward is the score of the game. Reward is the scores, and the state is the screenshots. The actions are the directions buttons of the joysticks. DeepMind was very ambitious. They want to create a general intelligence, so they didn't pre-process the game screenshot. They didn't try to label the objects or enemies. They just send the state, the whole screen into the model. So they just use the raw pixels of the screenshot as their input, as their state. So this makes the possible states very huge. The number of possible states is very large. The breakthrough of DeepMind's DeepQ learning is to use neural network to approximate the Q table. DeepMind adopts a small neural network that has only 3 convolution layers and 2 fully connected layers. Surprisingly, the simple network can successfully learn many different Atari games and achieve human-level performance. Here is the table extracted from their original paper, which shows the parameters of each convolution layer and the fully connected layers. So for convolution 1, the input size is 84 by 84 by 4, which is the screenplay of Atari game. And they first use larger filter size, 8 by 8, then reduce the size. Also, they first use a large stride. Okay, as common CNN, the number of filters increase with the depth of the layers. The final output dimension is 18, which are directions plus the fire button. So there are 18 output selection. Both reinforcement learning and the neural networks are hard to train. DeepMind introduced 2 tricks that make training DQN stable. The first trick is experience replay, which stores the previous action states and reward, which are called trajectories, and provide them again for later training. This trick allows DQN to review important actions and decouple the high correlation of continuous actions. The second trick is to use off-policy strategy. So they have a fixed target network, which can separate learning into behavior policy and target policy. They update the target network every 1,000 steps. In other words, if we only have one network, calculating the network, calculate the network will depends on the network parameter can change quickly and is unstable. Updating it every 1,000 steps increase the stability of training process. Actually, as we know, Q-learning is off-policy network, so it's naturally to have a fixed target network. So they compare the effectiveness of those two tricks. If we train without using those two tricks, actually we will fail. On breakout, the score is very low, so it's not working. However, if we add the target trick, fix the target network trick into training, then it will increase to 10.2, but it's still not working. However, if we add only the experience replay to the training process, it immediately increased to 240. So it works with experience replay. So it's very tricky if the author didn't find those two tricks. It can only the deep learning, the neural networks model cannot be trained successfully on Atari games. The most famous success story of DeepMind is AlphaGo. In 2016, AlphaGo won the 5-game Go match against the 18-time world champion Li Sudong, and lost only one game, which is the last game won by human. After this match, AlphaGo has swept the human opponents. No professional Go player can win AlphaGo right now. Go was considered the holy grail of human intelligence because previous algorithms can only beat mature players. This is indeed a great achievement in human history. Actually, there's one Taiwanese that worked for the AlphaGo team. His name is Aja Huang. He studied PhD in National Normal University. David Silver, the previous professor who taught the best reinforcement online course and now working in DeepMind, find the paper of Aja Huang and very impressive about his work of Go. So he invited Aja Huang to work in London, and they published the paper of AlphaGo together. Aja Huang is the first author of AlphaGo, and he is the hand of AlphaGo when playing against Li Sudong. Here's the photo when Aja Huang is playing for DeepMind, for AlphaGo. DeepMind continued pushing the limit after beating the human world champion. In October 2017, DeepMind introduced AlphaGo Zero, which learns Go without referring any human play records. In other words, it's starting from scratch, so it's called AlphaGo Zero. Eventually, no one can understand the strategies behind the moves of AlphaGo Zero, which are beyond human comprehension. Let's see the learning progress of AlphaGo Zero. The AlphaGo Zero has no prior knowledge of the game and only the basic rules as input. After 3 days, AlphaGo Zero surpassed the ability of AlphaGo Li, the version that beat the champion Li Sudong in 2016. After 21 days, AlphaGo reached the level of AlphaGo Master, the version that defeats 60 top professional online and world champion Ke Jie in 3 out of 3 games in 2017. After 40 days, AlphaGo Zero surpassed all other versions of AlphaGo and arguably becomes the best Go player in the world. The latest work from DeepMind is AlphaStart, which learns to play the famous real-time strategy game StarCraft. Although StarCraft is easier to play than Go for most people like me, it is partially observable game and hard for reinforcement learning. In the beginning of the game, the map is covered with war fog, and each player can only see the neighborhood of his own troops. On the contrary, Go is a fully observable game that all components' moves can be viewed. Therefore, StarCraft is actually more difficult than Go. After 1 or 2 years of AlphaGo 0, DeepMind managed to meet AlphaGo star, which also beat the human master. To learn in reinforcement learning, we first need to have a good environment. Fortunately, the OpenAI has created many environments for us. So the OpenAI G is the most popular reinforcement learning benchmark for the researchers. We will use OpenAI Gene for our homework and tutorials.
We're working on teaching robots to solve a wide variety of tasks without having to program them for any one specific task. Here, a robot has learned to rotate a block into any orientation we'd like. Once it succeeds at that, we give it a new goal, and so on. The system runs on a human-like robot hand, and we use reinforcement learning and simulation to teach the robot how to solve tasks in the real world. To learn how to solve a task like this, we show it many different variations of the world, where the rules are slightly different every time. This is a technique called domain randomization, and it affects, for example, the color of the cube and of the background. However, we take this technique beyond just how the environment looks. We also randomize aspects like how fast the hand can move, how heavy the block is, and the friction between the block and the hand. Our learning algorithm sees all of these different worlds, and this lets it learn a way of manipulating the block that is very robust. Robust enough so that, eventually, we can accomplish the same task in the real world. To simulate all of these possible variants of the environment, we've built a system that runs the training processes in the cloud on thousands of machines. It's called Rapid, and we've used the same system before to solve complex video games. First, rollout workers collect experience from many different variations of the environment. They send this experience data to the optimizer, which uses it to improve the parameters of the model controlling the robot. Finally, updated parameters make their way back to the rollout workers to complete the cycle. One thing that's very interesting to us is how general the system is. Not only can it rotate blocks, but it can perform tasks with other shapes as well. If you wanted to write a controller for this task the old-fashioned way, you'd sit down and write out exactly, if I'm in this position, move this finger in this direction. If I'm in this other position, move here, and so on. It's very meticulous. Instead, our system can learn to manipulate objects of all kinds of shapes without any additional human help. We hope that with this approach, we can solve more and more complex tasks in the future, so that we can go even further beyond what today's hand-programmed robots can do.